Hello, Matt here from chemistrystudent.com. In this video, we're going to look at the oxidation of alcohols. We're going to talk about what happens when primary and secondary alcohols are oxidized, the conditions needed for such reactions, and why tertiary alcohols are unable to be oxidized. Testing for aldehydes using Tollens reagent or Fehling solution is also discussed. Before we talk in detail about the oxidation of alcohols, there are a few essential ideas you need to be comfortable with. Alcohols are a type of organic compound that have an alkane backbone and a hydroxy OH group bonded to one of the carbons. For simple alcohols, they are basically an alkane where an OH group has been swapped for a hydrogen. Alcohols can be primary, secondary, or tertiary, depending on where the OH is bonded to in the carbon chain. Primary alcohols have an OH group that is bonded to a carbon atom that is bonded to only one other carbon atom. Secondary alcohols have an OH group bonded to a carbon atom that is bonded to two other carbon atoms. And tertiary alcohols have an OH group bonded to a carbon atom that is bonded to three other carbon atoms. Aldehydes are compounds that contain a carbonyl COO bond at the end of a carbon chain, with a CH bond to the same carbon. Ketones are compounds that contain a carbonyl COO bond that is in the middle of a carbon chain. Carboxylic acids are weak acids that contain a carboxyl group, COOH. Recap done? Let's go. Oxidation in organic reactions can seem very confusing. We can't see electrons moving in the same way as we can for inorganic processes, like metal atoms losing electrons when oxidized. At this level though, oxidation in organic chemistry refers to a carbon atom gaining bonds to a more electronegative element, nearly always oxygen, and or losing bonds to a less electronegative element, nearly always hydrogen. Meaning for this level of study, we can think of oxidation reactions in organic chemistry as being a carbon atom gaining a bond to oxygen and losing a bond to hydrogen. Equally, we can refer to reduction in organic reactions as the loss of a carbon-oxygen bond and the gaining of a carbon-hydrogen bond, so just the opposite of oxidation. Alcohols can be oxidized. The oxidation process is often just represented with square brackets and an O, as the focus is on what happens to the organic molecule rather than the reagents reacting with it. In the oxidation reaction of an alcohol, it is the carbon bonded to the OH group that is the center of attention. For this carbon to gain another bond to an oxygen atom, a carbon-hydrogen bond must break, otherwise the carbon would form too many bonds. As a carbon-hydrogen bond to this carbon breaks, the carbon is able to form a double bond with the oxygen from the OH group. That itself loses its hydrogen. This is classified as oxidation as the carbon atom is gaining a new bond to an oxygen atom. Even though it was already bonded to this particular oxygen, it now has a double bond to it, whereas before it was a single bond, meaning it has made a new bond. A carbon-hydrogen bond also got broken. Carbon-oxygen bond getting made, carbon-hydrogen bond getting broken, hey presto, an oxidation reaction. For a primary alcohol, this process would form an aldehyde, and for a secondary alcohol, a ketone. The interesting thing here is, however, that the carbon in an aldehyde still has a carbon-hydrogen bond that can be broken, meaning it can actually be oxidized again and make another carbon-oxygen bond. Oxygen is unable to make triple bonds, meaning the oxygen already double bonded to the carbon can't make any further bonds to it, and a new oxygen atom is needed. And as the carbon can only lose one more hydrogen, the carbon will only be able to make a single bond to this new oxygen. As oxygen makes two bonds, however, a hydrogen will end up bonding to this new oxygen and an OH group will end up bonded to the carbon. This produces a carboxylic acid. Again, this is oxidation as the carbon has gained a new bond to an oxygen atom and a carbon-hydrogen bond got broken. The ketone formed by the oxidation of a secondary alcohol is unable to be oxidized again, as the carbon of interest has no carbon-hydrogen bonds left that can be broken and already has 4 bonds. 2 single bonds to other carbon atoms and that double bond just formed to the oxygen. If it tried to make any more carbon-oxygen bonds, it would end up with more than 4 bonds, and this is impossible. This is why secondary alcohols can only be oxidized to ketones and can't be oxidized further. If we look at a tertiary alcohol, there are no carbon-hydrogen bonds that can be broken to start with, and the carbon bonded to the OH group is unable to make any new bonds with an oxygen, meaning it can't be oxidized at all. This is why tertiary alcohols don't undergo oxidation reactions. For example, propan-1-ol is a primary alcohol that can be oxidized to form the aldehyde propanol. The carbon bonded to the OH group in the alcohol loses a carbon-hydrogen bond and makes a new bond to the oxygen from the OH group, forming a double bond and making an aldehyde. If the conditions are right, this aldehyde can then be further oxidized to a carboxylic acid, as the carbon atom double bonded to the oxygen still has a carbon-hydrogen bond left over that can be broken, enabling it to form a new carbon-oxygen bond by bonding to an OH group, forming propanoic acid, a carboxylic acid. Propan-2-ol is a secondary alcohol that can be oxidized to form the ketone propanone. Again, the carbon bonded to the OH group in the alcohol loses a carbon-hydrogen bond and makes a new bond to the oxygen from this OH group, forming a double bond. As this COO bond is in the middle of the carbon chain, a ketone rather than aldehyde is formed. There are no carbon-hydrogen bonds left to break on this carbon, and the carbon is unable to make any new bonds to another oxygen atom, meaning no further oxidation can occur. 2-methyl-propan-2-ol is a tertiary alcohol that can't be oxidized at all, as the carbon bonded to the OH group has no carbon-hydrogen bonds that could be broken and already has 4 bonds. To oxidize a primary or secondary alcohol, an oxidizing agent is needed. A common oxidizing agent used is acidified potassium dichromate. Acidified just means in acidic conditions, as in potassium dichromate in acid. Often dilute sulfuric acid is used. This is why H+ is shown with the dichromate ions when writing out such reactions, representing the acidic conditions. If an oxidation reaction occurs using potassium dichromate, the dichromate ions, Cr2O72-, get reduced and Cr3+ ions are produced. Dichromate ions are orange in solution, whereas Cr3+ ions are green. This means when primary and secondary alcohols are oxidized by the use of potassium dichromate, a color change of orange to green is observed. As tertiary alcohols can't be oxidized at all, when heated with acidified potassium dichromate, no color change occurs and the solution would remain orange. Conditions of heat are also needed to get the oxidation reactions to start. When a primary alcohol is initially oxidized whilst being heated, the high volatility of the aldehyde formed means it will leave the reaction mixture as a vapor. If this vapor is caught and condensed using distillation, this vapor can then be isolated as a liquid and the aldehyde obtained. If a carboxylic acid is desired, however, the aldehyde must remain in the reaction mixture and keep being heated with the oxidizing agent. To do this, reflux conditions are used. For reflux conditions, a condenser is placed directly above the reaction mixture being heated. This means as vapors of the aldehyde rise out of the mixture, they are cooled and condensed into a liquid, and then gravity will cause the condensed liquid to fall back into the reaction mixture. This means no aldehyde is lost and is forced to keep reacting until it is all oxidized fully to a carboxylic acid. Secondary alcohols only have one product of oxidation, meaning it doesn't really matter if distillation or reflux is used to obtain the ketone. For primary alcohols, however, it is important to remember that to get the aldehyde, distillation must be used, and to get the carboxylic acid, reflux conditions must be used. A common exam question and requirement at this level is to be able to determine whether an alcohol is primary, secondary, or tertiary based on oxidation reactions. Let's imagine you've got three samples, A, B, and C. One is a primary, one is a secondary, and one is a tertiary alcohol. To find out which is which, we need to try and oxidize them all and then analyze the products formed. To start with, they would all be heated with acidified potassium dichromate, the oxidizing agent. The primary and secondary alcohols would be oxidized and therefore the dichromate ions present would be reduced, and a color change of orange to green would occur. The tertiary alcohol won't undergo oxidation at all, and this means that the solution will remain orange. The solution that remains orange at the end therefore must be the one that contains the tertiary alcohol. In this example, A. Now we need to distinguish between the primary and secondary alcohol. By heating the two solutions left, B and C, with acidified potassium dichromate and distilling the products, we ensure that the primary alcohol only goes to an aldehyde. This means one of the distillates now contains an aldehyde and the other a ketone. There are two tests we can use to confirm the presence of an aldehyde: Tollens reagent and Fehling solution. Ketones don't give a positive result for either, only aldehydes. If an aldehyde reacts with Tollens reagent, a silver solid is formed, often referred to as a silver mirror, as it coats the inner surface of the container being used. And if an aldehyde reacts with Fehling solution, a brick red precipitate is formed, copper 1 oxide, from a blue solution. These reactions have been outlined in more detail at chemistrystudent.com. Check the links in the description below. Now, whichever distillate from oxidation gives a positive result with either of these tests must be the aldehyde and therefore must have come from the primary alcohol. In this case, B. That means B is the primary alcohol and C be the secondary alcohol that produced the ketone. So, to summarize, primary and secondary alcohols can undergo oxidation reactions when heated with an oxidizing agent. They can gain a carbon-oxygen bond and lose a carbon-hydrogen bond. Tertiary alcohols are unable to be oxidized. An oxidation reaction can be represented using square brackets and an O. Primary alcohols can be oxidized to aldehydes and then further oxidized to carboxylic acids. To obtain an aldehyde, distillation is used, and to get the carboxylic acid, the reaction mixture is heated under reflux. Secondary alcohols can only be oxidized to ketones. An oxidizing agent is used, usually acidified potassium dichromate. The solution changes color from orange to green as chromium is reduced to Cr3+ ions during the reaction. We can test for aldehydes using Tollens reagent or Fehling solution. If a color change occurs, then an aldehyde is present and the alcohol oxidized to form it must have been a primary alcohol. For Tollens reagent, a silver precipitate or mirror is formed, and for Fehling solution, a brick red precipitate is formed from a blue solution. I hope you found this video useful. Please check out other relevant videos in the links given in the description below and visit chemistrystudent.com for free notes and revision materials.